All right, so let's continue talking about mathematical induction. So last time we introduced the concept of mathematical induction. So we said that there are two steps of a proof. So we usually have a propositional function P of n. And in order to prove a statement, a propositional function using mathematical induction, so we have two parts. So the first part comes from the base case in which we have to show that the first step is true. So if we have, for example, for all n and n, we need to show that P of 1 is true. So that's the base case. Then in the inductive step, we have to assume that for all k in n, if P of k is true, then we had to show that the next step is true. So we would have to show that P of k plus 1 is true. So those are the basic steps of mathematical induction. So we had a look at a couple of examples last time. So this time we'll have a look at some more examples. So this example here involves the use of inequalities. So we want to use mathematical induction to show that this statement is true. So in this case, our propositional function should be this statement for all positive integers n. All right, so let's start with the proof. So proof. Okay, so let's see. So we're first off gonna say, well, let P of n be this statement defined by n is smaller than 2 to the n for all, or just this statement for n in the natural numbers, which is the same as saying for all positive integers n, all right? So now we just have to show the base case. So the base case, we show that P of 1 is true. So P that P of 1 is true. So on the left-hand side, so P of 1, what does that mean? Well, P of 1 just means, well, on the left-hand side, we just have 1. And we're saying that, well, this is less than 2 to the power 1, which is equal to 2, which is true. So which is true is true. So therefore, we completed the basic step. So completing the base case. Okay, so that's the base case. Now we have to move on to the inductive step. Okay, so this step, we start with the following. So assume that for all k in n, that P of k is true. So what does that mean? i.e., well, by the inequality, well, what does pk mean? So P of k is saying that, well, k has to be less than 2 to the k. This is what we're assuming. So this is our inductive hypothesis, which I'll label this in green. So this is our inductive hypothesis. So now we had to show that. So we want to show that P of k plus 1 is true. And what does that mean? Well, we want to show that, well, what does pk1 say? Well, this says that k plus 1, this has to be less than 2 to the k plus 1. So that is what we want to show. So I'll label this as goal. Okay, so let's work with the left-hand side first. Well, indeed, if we have a look at the left-hand side, we start with k plus 1. But by the inductive hypothesis, because k is less than or equal to k plus 2 to the k, then that means that, well, k plus 1 has to be smaller than 2 to the k plus 1, right? But another thing that we could use in this case, well, because 1 is smaller than 2, I could also say that, well, 2 to the k plus 1 is smaller than 2 to the k plus 2. Now, this is still true. So I'll label the part where I use my inductive hypothesis. So this is the stage where I use my inductive hypothesis on k to go from k plus 1 is smaller than 2 to the k plus 1. And then I use the fact that, well, I could actually change 1 or make 1 because 1 is smaller than 2. So I could use that fact and make this right-hand side as is right now. So from here, at this stage, I could common factor out to 2 and write this as 2, times, actually, there's one small mistake here. So actually, this is actually smaller than 2 to the k. Well, it happens all the time. So you could also say, for example, well, 2 to the k is smaller than, or plus 1 is smaller than 2 to the k plus 2 is smaller than 2 to the k plus 4, and so on. You could say until, well, into the kth one, it's smaller than 2 to the k. So this is a little bit of an induction step. So you could also see that, well, this is always going to be larger than this one, or smaller than this one, and so on until you reach this stage. So this is the part where we could actually common factor out now, the 2, or we could write this as 2 times 2 to the k. And because we're multiplying two numbers of the same base, I could add their exponents. So this becomes 2 to the k plus 1. So therefore, we completed the inductive step. Okay, so therefore, by mathematical induction, we have shown that n is smaller than 2 to the k, or 2 to the n, for all n and n. So that completes the proof for this one. Okay, so this one's not too bad. So it's just a little bit of a trick that you would have to be able to observe. So this is one key fact that one should be able to observe as well. Okay, so let's move on to the next example. So use mathematical induction to prove that 2 to the n is smaller than n factorial. Now, notice that, well, here we have for every integer n greater or equal to 4 now. So it's not true for 0, 1, 2, or 3. So now our starting value is going to be at 4 now, right? So let's get started with this. So let's start with the proof. So our propositional function, so we're going to say let Pn be the propositional function that 2 to the n is smaller than n factorial for n in Z with n greater or equal to 4. So that's our propositional function. So now we start with the base case. Okay, so now our base case here, because we're actually going to be starting at 4 here, that means we need to prove P of 4 is true. So we show that P of 4 is true. Now, what does P of 4 say? Well, here, we're saying that here, well, P4, what this says is that, well, 2 to the 4, which is equal to 16. This is smaller than, well, 4 factorial, which we know if we calculate this, this is 24. So clearly 16 is smaller than 24. So therefore the base case is true. Okay. So now for the inductive step. So one thing we need to do now is prove the inductive steps. And so let's see what it says. So assume that for all n or k in Z with k greater or equal to 4, that pk is true. I.e., so what does that mean? So we're saying that, well, for all k greater or equal to 4, that, well, 2 to the k is smaller than k factorial. So this is our inductive hypothesis. So I'll write that down. Okay, so now we just need to show that. So we want to show that P of k plus 1 is true. So we want to show that this is true now. Okay, so let's see. What does pk plus 1 say? So i.e., we want to show that this happens. K plus 1 factorial. Okay, so let's see what happens. So indeed, well, let's start with the left-hand side. So 2 to k plus 1. Obviously, we could write this as 2 to the k times 2 to the k, 2 to 1. But by the inductive hypothesis now, we know that 2 to the k is smaller than k plus k factorial, right? So I'm going to say, well, that's going to be k factorial times 2. Well, one thing I could also say is that, well, 2 in this case, we know that 2 is smaller than k plus 1 because here, well, k is 4, right? And k is between 4 is an integer that's larger than or equal to 4. So this inequality will always hold. So when that is the case, I could also say that, well, this is also smaller than k factorial. And this is multiplied by k factorial of k plus 1. So by definition, we know that we could write k plus 1 times k factorial as just k plus 1 factorial. So then that means I could write this as this. So this is the step where I use the inductive hypothesis. And I also made a note that, well, I could write 2 is smaller than k plus 1. So therefore, we completed the basis step. Therefore, we completed or proved the inductive step. And so, by mathematical induction, we have proven or shown that 2 to the n is smaller than n plus or n factorial for all n in Z with n greater equal to 4. So that is our proof for this example. Okay, so now let's have a look at one more example, but this time we want to have a look at something that involves divisibility. So now we want to show that, prove that n cubed minus n is divisible by 3 when n is a positive integer. So this is going to be using mathematical induction again. So let's have a look. Okay. So proof. So we first state our propositional function. So our propositional function is that 3 divides n cubed minus n. So that's what divisible by. So this is the notation we use when we want to state that something is divisible by the other, or in our case, 3 divides n cubed minus n, where n is a positive integer. So the base case here we prove the base case. So we want to show that P of 1 is true. And what does P of 1 say? Well, P of 1 says that, well, 3 divides 1 cubed minus 1, which is equal to 0. Now, we know that is true because we know that there is some integer k such that 0 is equal to 3 times k. In our case, k has to be 0 in order for the statement to be true. So in particular, when k is 0. So therefore, the base case is true. Okay, so that's good. We proved the base case. Now, let's assume, so let's write down the inductive hypothesis or inductive step. So assume that for all k in n, that P of k is true. i.e., so what does that mean? So we're saying that, well, pk is true. So that's saying, well, 3 divides k cubed minus k. Now, by definition, so i.e., furthermore, there exists some positive integer m such that k cubed minus k, this is equal to some multiple of 3. So 3 times m. So this is one key factor that we're going to be using. We want to show that p of k plus 1 is true, i.e., p of k plus 1 says that 3 divides k plus 1 cubed minus k plus 1, i.e., so furthermore, there exists some positive integer, or exists some integer, let's call it L, such that k cubed, or k plus 1 cubed, minus k plus 1, this is equal to 3 times L. That's what we want to show. So indeed, so let's see. Let's expand the left-hand side. So if we're saying that this happens, so let's rewrite the left-hand side first, or this side. So here we have by the binomial expansion, so we could write this as k cubed minus or plus 3k squared plus 3k plus 1, and this is minus k plus 1. Okay, so if we simplify this, this will give us k cubed plus 3k squared, and then minus 2k. And we could now common factor out some terms. Yeah, so we could write this as, actually, no, hold on. Because I could also write this as k cubed, sorry. So let me keep what I had. So I could write this as, so we have this statement. Now I could also write k cubed minus k for the first term. And then we have everything else. So the other terms are just going to be plus. So we have the 3 outside still. And we have the k squared plus k. So that is what we're left with now. Okay, so by the inductive hypothesis, we know that 3 divides this now, right? So because by the inductive hypothesis, which will put this as equal, and IH, we know that this is equal to 3 times a multiple of m, right? But now I could say that this here is 3 times k squared plus k. And now common factoring out the 3, I have k squared plus k plus m, right? So what does that mean? Well, we're saying here the right-hand side, which originally was k plus 1 cubed minus k plus 1. This original statement, we're saying that is equal to 3 times this. So what by definition, of divisibility, we have that 3 divides k plus 1 cubed minus k plus 1. Therefore, completing the inductive step. So therefore, uh, 3 divides n cubed minus n for all n. So there we completed the proof. Okay. So that is going to wrap things up for mathematical induction. So we went through plenty of examples. So the first example that we went through was the sum of first n natural numbers. The next example we went through was series progression. Then we looked at the inequalities, two different inequalities, and then we had to look at one that involves divisibility. So that's going to complete this series of mathematical induction. So hopefully, guys, you understand the concept of mathematical induction a bit better. So yeah, that's going to wrap things up for today, and I'll see you guys soon.